Thanks for attending. I'm Ryotaro. Today I will talk about our works to implement LoopInterchange to accelerate the vectorization. Sorry. LoopInterchange is a type of loop transformation to improve typically the locality of reference as shown in the bottom right example. So LoopInterchange is implemented the path named LoopInterchange in LLVM, and the path itself has existed for about 10 years, but it is disabled by default. Recently, there is a community. There is an activity in the community to enable it by default, and so if you are interested in, please refer to the link. So, but in this talk, I will talk about how to implement, how to increase the opportunities of vectorization by utilize LoopInterchange. So this is an example of how LoopInterchange improves the vectorization. Please note that I don't talk about outer loop vectorization, and in this talk I will focus on only inner loop vectorization. So under this assumption, in this example, so as for the J loop, we have loop carried dependencies. So we must execute each iteration of the J loop in sequential order. So it means we cannot vectorize the J loop without breaking the original semantics. On the other hand, the I loop doesn't have any loop carried dependencies, so it means that we can execute each iteration in parallel, and it also means we can vectorize the I loop. So exchanging these loops can makes the entire loop vectorizable if we only consider the inner loop vectorization. So this is just a simple example to explain how the loop interchange works, but there are many other various cases that loop interchange can enhance vectorization. So I will talk about our works to support such cases. So before going to the concrete, before going to the works, let me explain the current algorithm of loop interchange in LLVM. So loop interchange is not just a loop path, it is a loop nest path. So it reorders all loops in the loop nest. So it can reorders not only 2 loops, it can reorders 3 or 4 or 5 or more loops. So the left code shows the shortcode to show us overview of an algorithm that currently implemented in loop interchange. Oh, excuse me. Loop interchange aims to optimal orders of loops by repeatedly swapping 2 loops in a loop nest. And each pair of 2 loops is exchanged if we can prove it is safe and we consider it is beneficial or profitable for some reason. So to enhance vectorization by loop interchange, we must improve both the legality check, so its legal function and its profitable function. So from here we talk about what we worked for both functions. The first one is legality check. So this example shows us an overview of what legality check does. So This is a bottom left example. In this case, there are 3 loops, and the array A is accessed in the loop body. So we don't have any loop carry dependencies for the I loop, and we have forward dependency for the J loop, and the backward dependency for K. It is encoded to a data structure called direction vector, as shown in the bottom center of this slide. So the mark equal means we don't have any loop carry dependencies, and the mark less than means we have positive dependency, and the mark greater than means we have negative dependencies for the loop. So we deem exchanging 2 loops is legal if after exchanging the corresponding elements or in the vector, it is still lexicographically positive. Then we deem such exchanges legal. On the other hand, if exchanging 2 loops makes changes the lexicographical order, we reject such interchange. So in this example, exchanging the I loop and J loop is legal because, as shown in the bottom right, exchanging it doesn't change the lexicographical order. On the other hand, exchanging the J loop and K loop changes the lexicographical order, and it becomes lexicographically negative. So in this case, we reject this exchange. So this is what we did to improve this legality check. So previously, the legality check was too conservative, so some legal exchange was rejected. The bottom left one, the example is a typical case what was rejected previously. So focusing on the outermost loop, namely the N loops, we must assume this loop has loop carrier dependencies with all directions. So we have to mark it as star. And in this case, we cannot assume any lexicographical direction for this direction vector. So the problem of previous implementation is we must we check the entire lexicographical order for when exchanging some 2 loops. However, if we just want to exchanging the I loop and J loop, we don't have to consider about the outermost loop dependencies. So we submitted patch to relax the restriction of this legality check, and now this loop can be exchanged. And the fix. There are any other patches to fix corner cases, but this is not related to enhancement to enhance vectorization, but it was necessary to enable LoopInterchange by default. Okay, so the next one is profitability check. The profitability check of the LoopInterchanges consists of multiple rows, currently cache access and instruction orders and vectorization. And in the perspective of vectorization, there were two problems. The first one is that the priorities of these 3 rows are fixed, so we cannot perform exchanges such as it is necessary for vectorization, but it is not good for cache access. That is, it will lost locality of reference. The second problem is that in the vectorization heuristic, because or we call a routine to check if we can vectorize the loop. And the routine was too conservative, and we only deem a loop vectorizable when the loop doesn't have any loop carried dependencies. However, if we only have loop carried dependencies with forward direction, we can also vectorize the loops. So these patches or what is to address these issues. And the last one is still under the review, but I believe this example can be exchanged after it is merged. So this is a simple experiment to show the improvements by our works. So the bottom left code fragment shows what are used to measure execution time in this experiment, and the right one is shows the result. So as you can see, I compared the execution time with and without loop interchange, and while changing the value of n, that is the size of array or trip count of each loops. So as you can see, in many cases, the execution time reduces about the performance improved about more than twice. However, there is a case that exchanging the loop cause performance degradation when n is equal to 2806. I think as I checked, the cache miss is fairly increased. So I think something like cache slashing occurs in this case. However, in many cases, it shows a good performance improvement. So I believe this result shows the potential of loop interchange. So finally, let me talk about future work. So the first and I think the most difficult and important one is more sophisticated vectorization heuristics. So currently we only check the direction of dependencies introduced by each loops. However, it is better to make them target aware. It means considering, for example, vector lengths or the cost of gather scatter maybe it is better to achieve better performance. I think some analysis was like loop access analysis does similar thing, but loop interchange doesn't use it, and instead it is the analysis named dependency info. So it is not so easy. And the second one is the phase order problem. This is a phase order problem rather than loop interchange itself. But as you can see in the right, performing loop interchange after distribution may provide a better result. However, in the current LLVM path pipeline, we cannot perform such transformation because loop distribute is definitely always executed after loop interchange. So the last one is supporting more loop patterns such as triangular loops, reduction variables, and more. So currently, I don't have a concrete plan to address these issues. So I'd be happy to discuss further if you are interested or you have any good idea. sorry. So this is a disclaimer upfront. So thank you.